Today we will discuss about the power electrons. This is the subject name is analog circuits, and we are discussing the module 5 of analog circuit. This is the power amplifiers. So we will see the content of power amplifier. In this classification we will see here class A power amplifier and its analysis. And then we will see the harmonic distortion, class B, the class B amplifier and postpone its analysis. All the class C we will see, and thermal stability. So introductions. What is the power? The power amplifier are used to deliver the relatively high amount of power, usually to low resistance load. Means maximum high amount of power we will deliver to the low amount of resistance. The amount is power to low resistance. Typically the value of that ranges up to 3 megawatt transmission and to 8 audio speaker. Generally output rating of will be 1 watt or higher. Minimum 1 watt rating should be. The ideal power amplifier deliver 100% power, but practically it is not possible. It does some usually supply to load, and it practice this. The reason for it, that's the component in amplifier will display some power rating. The concept of power amplifier. So it provides sufficient power, so good it deliver to large amount of power when the output resistance must be low. So deliver large for what is the power? Power is nothing but, we know the power is nothing but we know that power is nothing but power P equal to I square into R. P equal to I square into R. So P equal to, so how the power will be large? P is power P equal to I square into R. If the current is large, then power must be large. To deliver the large voltage to the large load and resistance is switching power supply to provide the low output resistance in order to avoid the loss gain and maintenance the linearity to minimize the harmonic distortion. To deliver the power load to the load efficiently. Block diagram of general power amplifier. So suppose the pre-amplifier is this. What is the function of this pre-amplifier? It amplify the low power signal. Low power signal. It amplify low power signal to high power signal. High power signal. It is the amplified low power signal to high amplifier. Suppose that here signal is in the range of millivolt, then it converted to rendered in volt. Suppose that 10 volt, 12 volt, etc, 3 volt port. So this is the generally power amplifier. This again voltage amplifier to improve. Here it may be output may be any signal current like this. Again we have to use the voltage amplifier that generally introduce the amplify the voltage. Neck tone and volume control wise, this in case of this is generally in case of audio input, these are in case of general amplifiers. This is the input, anything like this. This for example of. Next we will discuss about the power amplifier, how the power dissipation. In an amplifier total power, it is dissipated in a series circuit or parallel set of what is the, then total power must be added. So how we can calculate the power? The total power equal to P total is called the total power equal to individual power P1 plus P2, all everywhere power is dissipating, that power will be aid directly. So that power will be aid directly in circuit. Suppose that just P1, P2, suppose that P1 is investing here, how the current is going on, so P1 is there, this is the, here is a P1. So this is the P1 power is there here, power distribution P1, here power distributed is the PC, load current is that P. All resistance are connected distributed power here power. So we add the total power, and P is that emitter transistor power. So any circuit, this is the general concept for how to calculate the power in any power amplifier circuit. So different between the total value and generally from the load to, then we will calculate the, so how the total power will calculate based the power distributed power amplifier. Then power amplifier efficiency eta, a figure of merit of power amplifier efficiency eta. How we calculate the power? The generally power efficiency is the ratio of AC output power transistor, how much amount of AC power is dissipated, and 2 divided by DC power input. Any transistor has two types of power dissipated. First is AC, first is AC power. Suppose that AC power, and next is a DC power. So how they calculate the AC? So this is the AC power. This is the ratio of AC power dissipation to power of DC power dissipation. That is a called power amplifier efficiency. So the efficiency of amplifier is defined the ratio of AC output power delivered to load to DC input power by the formula eta, AC power divided by DC input power into 100. For efficiency in calculated in terms of percentage, we need to multiply 100. So the ratio of AC power divided by DC power based DC based transistor. As we will see, the certain amplifier configuration we have much higher efficiency rating than other amplifiers. This is the primary consideration when we are deciding the type of amplifiers we can use the specific applications. Suppose the power amplifier classification, we suppose this is the audio amplifier one. First is audio amplifier, then radio frequency amplifier. That amplifier works on the radio frequency, RF frequency. There is a very high range of frequency that amplifier will come. Again is a DC amplifier, the amplifier which amplifies the DC power. So that's the DC amplifier. We will see one by one classification of power amplifier. How the power amplifier can be classified. So this is the power amplifier, class A power amplifier. This is the class we are providing input is here, and big Q point is the center of the DC load line here. You can see this. So this is the output here. This is the output. This is the output form. This is the output signal. This is the output signal, and here is a input signal. Input signal. This is the Q point, because the Q point is middle of the load line. That's why here this signal is not clipped anywhere and distorted. Directly same signal appeared as the output here. This is the class B amplifier. Here in class B amplifier, what we are seeing here, the Q point look like this. The QNH conducting point here, this moves to the downward sides. This move to the x-axis at the VCC, and this is the input signal. This is the input signal like this, and we are projecting the output like this. This is the class C amplifier. We will see one by one. The transistor conducting during the whole cycle of sinusoidal inputs. This is the class A amplifier. In class B amplifier, transistor conducting during the 1/2 cycle of inputs. This is the output of class B amplifier. This is class C amplifier, transistor less than pi. This is the output up to here to here. This is the output, like conduction is less than pi here. Conduction is less than pi. We can see the conduction here is less than pi. Here conducted whole up to 2 pi. The class A amplifier. Class B amplifier, it is conducted only this period. Again this output is 0. So after pi to between the pi to 2 pi there is no conduction. So class A, we seeing the output is conducted whole complete one cycle. Circuit start from here, and here. This is the complete one cycle. Next, the class B amplifier, it is conducted just just here to here, just the one cycle. It is conducted up to here to here, just one cycle. And then we will discuss about the class C amplifier. This is the conducted less than, this is the conduction cycle less than pi in this class amplifier. Then class AB amplifier, the transistor conducts slightly more than half cycle inputs. This, suppose that this is the pi is here, it will conduct more than pi because pi is here only. This is the, so we have seen how the conduction is going on. First class A conduct the whole cycle, class B. So we will see about the conduction cycle, how the conductions. First class A amplifier whole cycle up to conduction cycle is 160. It is a conductor, we have seen up to whole period like this. This is the, suppose that this is conducted complete whole cycle up to here. This is the class A. Next class B is conducted up to pi. What we have seen, this is the class B, it is conducted up to here. We can see then class C, it is conducted less than pi. This is the class C examples we have seen either. This will conduct less than pi. This conduct less than this. This is the about the class C. And the conduction angle, this is the conduction angle. They will ask in the question in the conduction angle between, they will conduct the less than 60 to 180 to 360. Then quiescent point, how the quiescent to the is at the center point of the load line. This is the, we have seen this is the center point. This class A, this is the center point of the load line. This is the center point in class A. Mein conduction is a center point of load line. Yeah, this is the center point. This is the center point of load line. And next we will see about the exactly on the x-axis. We can see this is the class B. This is exactly on a, this is here exactly on the load line plus x-axis. So that exactly on the x-axis. Here this is exactly on x-axis. This is exactly on x-axis. Next we will see about the below the x-axis, and it moves towards the below the, this is the quiescent point in negative beyond the, this is the power class C I'm saying. So they will ask the class C amplifier. Then one class, this it between the x-axis and center load line, because here this is the between the class D, this is the between the x-axis. AB is not drawn here between, suppose that we will draw that it between the and x-axis. So suppose that this is the, we will draw the load line of the circuit like this, and we will draw like this. So this Q point up to in class AB amplifier, this is the class AB amplifiers, class AB amplifiers. So the Q point approximated up to QC up to here. So we will see conduction point. Then overall efficiency, the poor efficient, this is the efficiency is very less, because up 25 to 30%. Then class B improve the 70 to 80%, class C higher than 80%, class AB better than A but less than 50 to 60%. Signal distortion, none, one is correctly biased. At the x-axis crossover point is there. The signal none if the A correctly, there is no any type of direct whole signal is appeared here. You can see all complete signal is appeared at the output. It only amplified. And B crossover and B at the x-axis some crossover distortion is some here, some changes here, some crossover distortion may be here at the, this Q point at the x-axis. Some crossover distortion is nothing but here some output look like, suppose that this is the look like this and look like it. So go in some small lightly this and look like this. This is the called crossover distortion here. So this is not given to here. I'm explaining how the crossover distortion will here. Actually when we have draw this line, this is the class AB amplifier, this is the class AB amplifier, this is the AB amplifier, this is for A class AB amplifier. Then small amount of account, this is the here distortion, what AB में distortion very less is amount in class C में efficiency is very high, more than 90, efficiency is very high, more than 80%, but this is the again large amount of distortion below. That's why we will not use the C amplifier. Generally they will ask the question, compare the class A, class B, class C amplifier. Is sometimes they will write the property of class class A power amplifier, class B amplifiers. And next we will have class D amplifier. This it reduces their efficiency is reduced then compared to C, but the distortion is small amount because of we want to less distortion. That's why we have used the class AB amplifiers. Next, efficiency rating. So how they will efficiency rating? We have to they will ask the question, write the efficiency class A, class B, class C. So maximum theoretical efficiency rating class A amplifier, class B a class C amplifier. So maximum class A amplifier is maximum 20%, 25% amplifier. Class B is a 78%, and class C is a 99%. This is theoretical element. The practical is not possible to 99%, but theoretical they will ask the efficiency. That's why generally they will ask the theoretical efficiency of the power amplifier class B like this. Even the step to analysis of the power amplifiers. First, so some steps we will follow them to draw the graphical operating points representation, make DC and AC components a 0. Make the DC analysis, that time AC component must be 0. We are doing the DC because we need to calculate the efficiency. For efficiency we need to AC power and AC power. That time we will calculate this. The class A amplifier, how the class A amplifier is amplifying signals. Suppose this is the input signal, this is the class amplifier A, and this which has a gain AB. So it amplifies the input signal from here to here. And what is the phase shift? So here phase shift is here pi shift. Suppose that this is the input like this is the input, and this output is the amplified form. This output is amplified form, but it phase shift. It is the change the phase shift by 90 degrees. This signal reduce. This will be reduced form. That's so. This is the reduced form. That means we have to add the signals. Draw the line. This is the amplifier, then reduce the this is the just opposite, then compared to this is the pi phase shift. Here is also pi shift, pi with pi phase shift. That's why the output is amplitude is increased here and phase shift is a pi. So this is the amplifier. We have this again the output waveform. The output waveform shape is the output waveform shape the pi by 6. This is the collector current is non-zero. Because why the collector current is non-zero here? Because the collector current is non-zero. Collector current non-zero 100% of any time, because inefficient since because zero we are even input is 0, even that way it produces the collector, because sub transistor has on voltage, base emitter voltage also, and on because of this the power on because of this, so non-zero transistor dissipation power. So that's why dissipation power non-zero always. That's why current rest of Houston point condition. So we will discuss the classification of power amplifier. First, RC coupled amplifier. What is the RC coupled amplifier? Then we will see about the transfer coupled amplifier. So in RC coupled and transfer coupled amplifier, RC and transfer coupled amplifier, we shall see RC coupled amplifier, RC coupled class A power amplifier analysis. The common emitter voltage divider configuration RC coupled. This is the RC coupled amplifier. The circuit of also this is the VCC. The power supply VCC is there. This is the power supply VCC. This is the power supply VCC is here. Then this is the current IC is there. Then collector, this is the collector resistance. Collector, this is the collector resistance. Collector, this is the load. This line is a load. It's called a load. And this is the emitter resistance. This R is a emitter resistance. RE emitter and current I, and this is the AC input. This is the AC input. AC input is there. AC input. This is RC coupled amplifier. The type characteristics of curved class A amplifiers. A common emitter configuration. This circuit is designed for this is the suppose that input is given to here. This output we are taking here. So this input, this is the output. This is a class A. This circuit is a for class A amplifier. This is the class A amplifier. And this is the load line. So the DC load line at Q point at the center of the load line. Here this is the center of load. The intense power dissipation versus time of the transistors. So the power instance, how the power dissipation for any transistor, intense power dissipation, the current through the at the quiescent points, at the quiescent point we can see the that time quiescent current ICQ into VCC, or time supply voltage into VCC. This is the into VCC. So this is the called intense power. And intense power, we will see this like this initially. So initially they will multiply with here like this time period. This is the power signal. DC output. How do this circuit DC is for DC input power. Total DC power that an amplifier down the circuit supply. So DC, what the DC current going from this transistor ICC and VCC plus I1. What is this? The current going from here. And this IC is going from here and I1 is going from here. Then we can see ICC, your collector current is equivalent to ICQ because ICC is because ICQ is very high. Then this is the collector current. This is the generally less high because R1 and R2 value we have Q to too much high. After we are putting these values too much high, then we can see IC is equal to ICC key. So this is the ICQ is this is the ICC is equal to ICQ and ICEQ is greater than IC1. Note that this equation is valid most of the power amplifier. So we can how the DC power. So we can do the DC power ICQ into VCQ because ICP into VCQ because where we have neglected here I1 which is the flowing through here is neglected, and that's why this ICQ IC already ICQ. So this is the IC. That's we should know the DC how the DC power is calculated here. We have should then we calculate the DC power is nothing but what is the at quiescent point, what the current flowing through the transistor and supply voltage. This multiplication of these two things is called it DC power. Next we will see about the just the ideal. This is the case of ideal. We have then AC power. What is the AC power? How the AC power is nothing but output voltage. What is the for AC analysis? This is the equivalent circuit diagram for this circuits. This is the equivalent R1 and this is the equivalent circuit. This is the R1 parallel using the Thevenin. This is the R1 and R2 is a parallel to here. R1 and R2 is parallel to here, and this is the load. For this is the load is also parallel to here. Because if we draw the circuits RE and RL is a parallel, RC and RL parallel to here. For AC analysis, how will draw? Because this for AC analysis, this is the DC. All the DC inputs must be 0. How will we can draw this like circuit like this? Suppose that this is the transistor is there for AC analysis. we are making this for DC analysis, and input is like all the things we are making. So this RC and R, when we are connect grounded this is also RC and RL circuit look like a parallel in connection. So AC output RMS value and RMS value of IC current, and this is the IC, this is the AC circuits. So this is the RMS value, this is the RMS, this is the IC, this is the IC is going to here, and this is the VCC, this is the RMS value, this is the RMS value. So how calculate the RMS value, because signal AC for AC, because how to calculate the current and voltage RMS value. So for direct conversion, we know for if the signal is sinusoidal, for sinusoidal supported signals, we are providing sinusoidal signal like this. For sinusoidal signals, we calculate the output. This is the RMS value for input or current. This is the RMS equal to, how to calculate RMS equal to V see the maximum. Suppose this is the maximum. This is the maximum point is a VM. This is the maximum point is a VM. VM divided by root 2. VM divided by root 2. So any for this is the for the full wave RMS amplifier. Similarly, current is also we can calculate IM maximum current divided by root 2 for calculating. So memorize it. How we are doing this. So for memorizing, you have to memorize this. So IC is nothing but IM maximum current divided by root 2. So put this value for put this value here. So IC equal to, this is the value of IC equal to, this is the IC, and this is the value of RMS, and this value is, and we have to calculate this value here when we put. So VM by into, so root 2 into root 2. So VM divided by maximum voltage into maximum divided by 4 AC power. So what is the VM? The PP means peak to peak voltage. Suppose that this is the any voltage signal, and this is the this is the up to, this is the peak to peak, here to here is called it peak to peak signal, here to here is called it peak to peak signal, here to here peak to peak signal, that's is, or this is the called it VM, this is the called it VM. That's why VM equal to peak to peak, here to here divided by 2, because VM is just half divided by peak to peak signal. So this is the, that's why. So we can put the peak to peak value also here. So peak to peak 2 to multiply 2 is already, so 8 multiply 8 divided by 2. Here VP max is a VPP is equal to V max by V min. We can also call it V. This is the V max. This signal is called it. This value is also called V max. V max we can also set to V max, and we can also set to, this is the V min. This is the V min. VP min. So we can put this value here. Output AC equal to peak divided by peak to peak voltage and peak to peak input current divided by 8, because 2 into 2 multiply 8 divided by 2 is 8. Then efficiency, how we calculate the AC power? This is the AC power. So V max by divided by 28. So VCC. So we know efficiency AC power. We have already studied about the efficiency is nothing but AC power divided by DC power in percentage. So what is the AC power we have calculated from here? The PAC power V max minus V min into multiply I max minus I min divided by 8. So V max minus V min into I max minus I min divided by 8. Input DC equal to VC into ICQ. So V max minus V min, I max minus I min into 8 into VCQ into ICQ. This is the VCC into ICQ. We have all discussed the DC. This is the DC inputs from here. So we have taken this value from here to here, and So percentage 2 into VCC and ICQ, 8 into VCC and ICQ. Then how we decided the VCQ? Put this value here. What is the VCC here? VCC. So for class A amplifier, this is the 25%. After putting this value here, VCC. What is the VCC and VCC into ICQ? Advantage. So this is the class for class A efficiency for this for class A amplifier. This diagram. Next, what are the advantages? This circuit is simple and easy to design. Less number of components is there because less. Disadvantage is some power dissipation is more. Efficiency is very poor. Large power because of large power. Transfer coupled amplifier. This is the RC transfer. Some theoretical, and this is theoretical of efficiency of RC based coupled amplifier. A is limited up to only any type of class A amplifier. The efficiency must be maximum up to 25%. In practical, it less than up to 25%. Used for output power only up to 1 watt, and the transformer coupling can be increasing the maximum efficiency to 50%. Disadvantage of transfer coupled amplifier, expensive and bulky. This is the RC coupled amplifier. Neglecting the transfer resistance, assuming RE 0. So this is the transfer coupled amplifier. What we have discussed as the RC coupled amplifier. Only here will changes. For in case of transfer coupled amplifier, this is the transfer coupled amplifier. So this is the DC load line, slope 1 by RE, and this is the DC load line. This is the DC slope of this 1 by RE. For AC load line, slope of 1 by RL. This is this circuit of RC coupled amplifier. Sorry, a transfer coupled amplifier. So here is only new is this RC coupled, and how this RC coupled will. Suppose that this is the input, this RL is there, and this is the N1 number of turns N1, and here number of turns N2. This is the primary coil, current is flowing I1. Here current is I flowing. And this is the load. So this we know the concept of transformer. This is from the concept of transformer. This is from the concept of transformer. Means this is the input voltage. What is the V1 divided by what is the V1 and primary turns? This is the voltage on primary turns in here. This is the suppose that is here. The V1 is here. Suppose that V1 is here and V2 is here. So this is the V2. So this is the voltage, primary voltage divided by secondary voltage is directly proportional to primary turn N1. Here is primary turn is N1. Here primary turn is N2. So we can see the voltage directly proportional to the voltage directly support to N. Suppose that V is proportional to the N. V is proportional means V1 divided by V2 is equal to N1 divided by N2. Next, here the current I1 is directly inversely proportional to V1. Means if the I1 divided the concept of transfer I1 divided by I2 equal to N2 divided by N1. Sometimes this is called primary. Somewhere this is also called primary. And this is called it secondary also. This is called it secondary. So V1, V2 and V. So that's why I1 if divided by the I1 divided by this is the suppose that I1 divided by I2. So V1 divided by V1 into I1 divided by I2. I1 by I1 if we take the ratios in. So I1 N1 divided by N2 square into V2 divided by I2. So we know I1 is V1 by I1 is R1. Reflective resistance is called it of input voltages. Here this is called a reflective resistance. E1 by R1 primary coil. We take the primary coil voltage and primary coil current. This is called it effective resistance of, and V2 is called it V2 by I2 is called it effective output resistance. Effective input resistance. This is effective output. Therefore RL equal to N1 divided by N2 into I1. This is the RL is primary here. RL dash is at the output voltage. So n is a number of turns in primary side and n2 is a number of turns in secondary side. The ratio we have taken n1 by n2 ratio, we have taken n, so we can write this. So the power amplifier may be matched by taking the proper ratio down. So DC input power, how do you, so total power DC input, that is amplified to the power. We have also studied DC, VCC is into IC, and IC is equivalent to IC, we have already discussed here. So this is the AC power, we have already discussed this. AC into DC, this is the case of maximum, we already discussed it. Power DC is total DC power plus AC power, total what is the. So in the case of class A amplifier, power DC based maximum when there is no input signal is applied, even because the efficiency can be some high as compared to series feed amplifier. The impedance matching is required for maximum power transfer. So due to the transfer coupled circuit become the bulkier and heavier and costlier as compared to series. The frequency response of the circuit is poor. The advantage is that no crossover distortion. No crossover distortion means class amplifier, suppose like this. No crossover distortion means what is the cross? It look like this. This is the called crossover. This region is called crossover distortion. Here there is no such type of problem in class A amplifier. No switching distortion is there. Any type of switching distortion. There is a lower harmonic components distortion in voltage, because distortion by the lower harmonic distortion, current voltage and current lower no signal depend on the distortion from the power supply. Constant and low output impedances. This one is low efficiency up to only 25%. Power dissipation more, even input is not applied. So we can see this, we will see the class B power amplifier. So the consist of the post pole amplifier and complementary amplifier and electronic devices. One conduct one half cycle and other conducted one another half cycle for half inputs. When the input is 0, both devices off and this bias and current are 0 and output is 0 and ideal voltage. This is the one transistor. You can consist of two post pole amplifier. So the for input larger than 0, then turn on the and supplies current goes through here. Input is larger, then current goes through here. One time this must be off and next time this must be. For input is less than 0, if input is less than 0, this input is less than, and then this transistor is on and its current comes from here. Positive half cycle, its current one transistor only. This is the transistor, this is the only this nothing we are connected in the transistor is here, and for input and on and sync current is also from here. This is the class B transfer coupled post pole amplifier. So this is the input transformer here. This is the transistor. This is the N pin. This is the P pin. If the input is supplies for positive half cycle, this will work. In negative half cycle, this will work. And this is the load transformer. This is the driven input transformer. How we calculate the DC load? For DC biasing, the point of x-axis. So the here for DC biasing, poison on the x-axis. This is the Q point. Q point is in on x-axis. So each transformer output is half rectified waveform, then peak value of output current DC. So for IDC is IM divided by pi 2. This is the called average value. Each transformer is worked for the half cycle. This is suppose that half wave, the concept we should know, half wave rectifier. For this is the suppose that pi, this is the half wave rectifier. So its DC current, DC output, we can say its DC output is nothing but IM total current. This is the IM divided by pi for I. For its RMS value will also we can calculate RMS equal to IM divided by VMI divided by I. This is the case of half wave rectifier. We should know these values. So for first transistor, Im divided by pi. For second transistor, Im divided by 2 pi. For total DC, Im by pi, 2 Im by pi. For full cycle, this is for DC, VCC into IDC. So VCC into IDC is nothing but 2 Im by pi. So we have already discussed the DC. VCC into IDC is nothing, ICQ for n transistor. For AC power, we know the AC power comes from I1 V1 into V1 RMS. So I2 into V2. So at the primary level for AC circuit, so V1 RMS into I1 RMS. Even I1 RMS, we can also write the power. We have write power formula. There are two power formula. First into voltage into current. This is one voltage. Another formula follows I square into R. R is a load. So same concept. This is the current I1 RMS. So we can use the I1 RMS. RL is a load. In another formula, we can also power has three formula, and VR voltage divided by a load, voltage square divided by. So this is one formula is here. Second formula is three formula. We can use the RL is a load. So for AC VM, for this is the for full cycle. This is the for I1 RMS. So VM divided by √2, and this is the V1 RMS equal to V1 divided by √2. So VM by 2. And another we can also write the I square into R. This value we know I square into R. Another we can also V square by RL. So three formula for calculating the power. Efficiency we also know AC divided by DC. And power AC equal to VM by 2 and power DC equal to VM upon pi, and put this value for efficiency, put DC, put this value here and this value here. So we can get this formula, percentage of pi by 4 into VM divided by 25. Maximum efficiency 25 for this power dissipation. This is the then complementary symmetry. B circuit is there. This is for this one. This is the NPN transistor. It works on if input is greater than this transistor is work if the input is greater than 0, and this transistor is work if input is less than 0, and we can see the output like this. Conductance Q1 slope like this, and conductor Q2 slope like this. So disadvantage we can see also. So this was the, and this is the crossover distortion is also to remove the crossover. We have complementary possible arrangement we can use to reduce the crossover. Class AB power amplifier. This is the class AB power amplifier. The small quiescent bias on each output transistor to eliminate the crossover distortion. These are used for eliminate the small biasing. We have provided above class B amplifier, so we can remove the crossover distortion free circuits, because it's small. We can use that here. One circuit. This is the tapped transformer hai, so crossover distortion we can use. So this is the class B amplifier. We have one conductor, one other cycle. So if the circuit transformer is less, then weight and size cost is high due to common collector configuration. Impedance matching is possible. Advantage of frequency response can be also improved due to transfer compulsion. Disadvantage is circuit is need to two separate voltage suppliers and two output buffers.